All right, now let's have a look at the things that we need to think about when we're training a neural network or a machine learning model in general. So I got a lot of this content of the next few slides from Andrew Ng's Machine Learning Yearning book, which is a very good reference if you want to delve into some of the details of what I'm about to see. It's a free draft is available on his website. Typically, when we're training machine learning models, we have a training data set, a development or dev set, and a test data set. Now, the training set is what we actually train the learning model, the learning algorithms on. Okay. A development set is used to tune the parameters of your model. This is something that is often omitted and forgotten by people. And then we have our test set, which is used to actually evaluate performance. As you'll see in the next slides, it's very important that we don't test our performance on our training set. Okay. So the dev and the test set is what guides changes and improvements to your machine learning system. Okay. It's important, hence, that you choose a dev and a test set to represent the future data that you want your model to actually work on. There's many strategies for splitting your data sets, and there is just no best split. Lots of people use 70% training, 30% test. There's tenfold cross-validation that you could do, whereby you split your data set in 10 folds, and then you're going to make a model for each of the 9 folds, all combination of each 9 folds, and test on the remaining fold. There's no best split. You have to see with what data you can benchmark with. Another model might have been developed and tested on a certain data set. You want to use the same data set, for instance. Now, there's a few common sources of error when we are training our models. Okay, first one is a data mismatch. It could be that you're training on the MNIST data set, which is small numbers. Number one, we'll look at this data set later. It's sort of the hello world of machine learning. But maybe the actual images that you're testing on have a different resolution. It's what we call data mismatch. Other sources of error include bias and variance. So bias is basically when you're underfitting, variance is when you're overfitting, meaning bias will give you low accuracy on the training set already. The model is just not learning what you want it to learn. Variance is overfitting, means it'll have a really good accuracy on the training set, but there's a large variance between the training set and the actual test set because it's not performing well on new data. It's overfitting. This is often represented in the tiny graphs that I put there. Overfitting will be like accurate prediction for every point or most of the points in the training data set. Underfitting just can't fit it. And you sort of need to find a good balance that works reasonably well for both new data and training set data. Because if you're overfit in the first graph, it works extremely well for the data that your model has seen, but this sort of very tailored graph does not perform well for new data typically. Okay. Do the test and the dev set come from the same distribution? Ideally, yes, they come from the same distribution, and ideally, they come from the target distribution. Let's take the example of the image, whereby you have a target distribution from a certain distribution, which is a dark red color here, and then you have another 100K images from the web. So they have a different distribution. What this distribution means? It means they might have a different size, different resolution. They might look a little bit different. Maybe they're black and white, the others aren't. Okay. So what you could do is you could shuffle them so that your training, dev, and test set, which is a 96-2% split here, all have the same distribution. It's good that they have the same distribution, but it's not optimal because you want your model to be optimizing for the target distribution. So it's not ideal here. Well, is this a better option? Let's make the dev and the test set come from the target distribution, but train on a mix of both. Okay. This is better, but it might be very hard to train your model now okay, to get good results on the dev and the test set. Okay. So it won't be easy to actually see if the error here comes from a variance error or data mismatch error or some sort of variation of both, a combination of both. Okay. So there's a better solution. We can use something called a bridge set. Bridge set consists of training data not used for training. Okay. This can be used to troubleshoot where the error comes from. In this case, we have 10% error on the dev set and only 2% error on the training set. Since if we train the bridge set, if we evaluate on the bridge set the same trained model, then we actually only get 1% more error. That 1% is the variance error, and that means that 7% of the error of the dev set actually comes from data mismatch error. So this classifier performs well on a data set that it hasn't seen before if it comes from the same distribution. It'll perform poorly if it comes from a different distribution. Hence, we have a data mismatch problem and we need to try to address that. Okay. So what if we have a high variance error? For instance here, we have a bridge set, same sort of setup, but now our bridge set has an error of 9% versus 3% previously. In this case, we don't have a big data mismatch error. Our data mismatch error is only the 1%. 70% of the error of the dev set is due to variance. Okay. So this means that our model is overfitted on the trained set. Let's look at another example. In this case, our bridge test set has 9% error. That means that only 1% of the dev set's error is due to data mismatch. Okay. Because if we use images of the same distribution, we still get a high error. So we have 7% variance error here. Okay. In this case, it means the classifier is overfitted to the training set. Okay. Now, how do we address all these errors? Oops. Here's a few rules of thumb. We can avoid underfitting by increasing the size of the model. Okay. This means in the case of neural networks, it means adding more layers, adding more nodes. We could modify the input features based on our error analysis. We'll talk about this a little bit later. We could reduce or eliminate regularization. We'll talk about regularization in a second as well. Or we could simply modify the model architecture, use a different type of model. Okay. In the case of overfitting, we'll want to add data to our training set. Add regularization, again. Add early stopping criteria, so that you stop when the model, if you imagine this overfitting graph again, that perfectly matches all of the training examples, you stop before the graph matches it exactly. Add feature selection to decrease the number of features, although this may increase the bias error. Decrease the model size. Again, this might increase the bias error. You could also modify again the input features based on error analysis or modify your model architecture. Okay. So it's really this balance between bias and variance error that you're going to have to address. Typically, measures like regularization will work pretty well. Okay. You could do, to get more training data, you could do artificial data synthesis. This is a way to incorporate characteristics of the dev and test sets into the training set. Okay. Maybe, for instance, if you have autonomous vehicle data, maybe you don't have cars available to drive around with you. What you could do is you could create a 3D computer environment, put a car in there, and record the camera of the virtual environment. It's a way to create synthetic data. Okay. If you are learning a problem, let's say speech synthesis, so you need to know if you have the text, you need to have the matching voice. So what you could do is you can actually synthesize the data with a model and then use this to further train perhaps your speech comprehension model. Okay. All right, so this is actually quite a challenge. It's hard to create data that appears realistic, much harder than it is to create data that appears realistic to humans, because computers can see much smaller differences. Think of this as systems that are trying to attack AI models. For instance, if you have an image classifier, you can totally fool it by adding like one black pixel in one particular place in all of the images you want misclassified. Something like one pixel that's always the same for one class and always different for another class can totally fool a machine learning model, but we won't notice it. Okay. So you could do error analysis. In this case, you want to analyze the errors on the def and test set and see how they're different from the errors in the training set. Okay. For instance, maybe you have images that are always misclassified. You're doing cat-dog classification, and you see that a group of images that are always misclassified is because there is a grassy background. Okay, that means maybe you need more images that have grassy background in your training set. So, as we mentioned before, we have our error, which is composed out of, it could be a variance error, it could be a bias error. But there's a third factor, which is the inherent noise in the problem itself. So this graph sort of shows you how the errors typically evolve based on model complexity. Mm-hmm. And the aim of our model is to find sort of that sweet white spot in the graph. Regarding the inherent noise in the problem, so it might not be possible for the model to properly capture the entire, all of the training set data and test set data. There might be some noise that it can't classify. This is typically captured by a random variable epsilon, which has a zero mean and a variance sigma squared of epsilon. So if we're measuring our error, a formula that's typically used, especially in regression problems, is mean squared error, MSE. And it's the average squared difference of a prediction from its true value. Okay. It's defined as below. If we look at, in this error value, what the subfactors are. First, we have bias. Bias is the difference of the average value of the prediction to the underlying function fx. Okay. There's a formula there for bias, which is basically just the predicted function minus the actual function. So this is measured for different realizations of the training data. What is a realization of the data? It means basically we only have access to a portion of the underlying data as our training data. Think of, for instance, we want to model the family income level and the house sale price in a certain neighborhood. Okay. If we had access to the data of every household, we would be able to build a very accurate model. But because this is just too costly, getting labeled data is very costly and time consuming, and there are privacy concerns, most of the times we just don't have all the data of the underlying population. So a realization is just a sample, whichever data we have access to from all of the underlying data. Okay. A second type of error that will be present is the variance error, which is defined as the mean squared deviation of the predicted value from its expected value, again, over different realizations of the data. Okay. So when we put it together, our error consists of our bias error plus our variance error plus our inherent noise factor. Okay. Again, if we were to plot this for a particular example, then we can see it appearing in a graph like this. Now, if we are training our actual models, we can plot the result of our accuracy or error measure on during our training process. Okay. So this is an example of a desired evolution of training and dev error loss. Okay. In order to plot this, you can simply plot the evolution of the loss after training X batches, for instance. Okay, we'll see this in the tutorial in PyTorch. Here's an example of a model that was trained, and the resulting model has a high bias error. Okay. What makes this high bias error? It's underfitting. The training error is much higher than we thought, and the dev error is usually higher than the training error, but most typically the training error is very high. Okay. It's important here to note that even if we add more training data, it just doesn't improve the result. Here's an example of a low bias, high variance model. In this case, the model is overfitting. Okay. It performs better than expected on the training set, but not on the dev set. Okay. So the training error is relatively low, but the dev error curve is higher than the training error. It's much higher than the training error. So the bias is small, but the variance is large. Okay. So it's overfitting and not underfitting at all. Here's a high bias and high variance error. In this case, the training error is very large again. The dev error is also much larger than the training set. So you have significant bias and significant variance. Okay. So we'll have to apply these measures that I mentioned before to reduce both these errors. An important technique that is very often used and that I haven't mentioned before is regularization. So in the plot on the right, you see an example of a very overfitted function. If the blue dots are all our training data, we see that the red curve almost exactly matches all of the red training data, almost too much so. Okay. So what causes this kind of overfitting and very curvy models? It's because there are many coefficients with a high power. So it's actually quite easy to regularize this. It's easily done by penalizing the weights of theta 3 and theta 4. If we drop that, the curve will be a lot smoother. Now there's two very common ways of doing this. There's more ways of doing this, but I'll just mention two very easy ones. First one is L1 regularization, which is also called lasso or L1 norm. Here we have our error function in the first term, as you see here. This is our mean squared error, and we add a term, the regularization term, which has the lambda regularization coefficient and the absolute value of all of the coefficients from the previous equation, the thetas. By adding this, you penalize high coefficients. Okay. So lambda here, if it's very large, it'll be strong regularization. If it becomes close to 0, then it's less regularized. L2 regularization or rich regularization, it forces the weights to be small again, but it doesn't necessarily make them 0. Why? Because this regularization looks at the theta coefficients to the power of 2. So it's this exact same setup whereby here we have the mean squared error, and again we add this lambda times the square of the coefficients. Typically, you'll see quite an improvement in your model and a drastic reduction of overfitting if you do these things. So next week, we'll be using Google Colab. I'll be sharing a notebook with you. Sorry, not next week, next class. We'll be looking at PyTorch and you'll be able to run all of the exercises in Google Colab. So if you don't have an account there yet, you might want to go ahead and create one. I will share the tutorial notebook with you and post more instructions on this.